Okay, so on this concept of determinism, I just wanted to give you a couple of pointers. I published a blog just a year ago, a single blog series that is kind of a short read on my position on determinism, and then a much longer paper that was invited as a sort of highlights paper or perspective paper, they called it, for the transactions on embedded computing systems. And I've also written a couple of books that are kind of philosophical. Determinism plays a pretty big role in these, and you'll get some sense of what that's about when I talk about it here. And then this more technical book, Introduction to Embedded Systems, talks a lot about it. But what is determinism? Well, in physics and philosophy, it's the principle that every action is a consequence of preconditions and some fixed set of rules. Okay? So there's a very closely related concept, which is causation. Right? The notion that the preconditions cause the consequences. But causation turns out to be a kind of a problematic idea. There's sort of a prevalent distaste for non-determinism in the physical world. And I think that this follows from a distaste for uncaused action. People don't like the idea that stuff just happens. Okay? There's got to be a reason. That's a very strong innate belief that it's got to have a reason. Okay? It's very hard to break away from it. I've actually been working on an argument that, that the reason that we have that belief is actually a consequence of evolution. It's not a consequence of properties of the physical world. I tried running this by someone actually just yesterday at the Human Sciences Institute on the other side of Vienna. A lot of very interesting people there. And she said to me, but wait a minute, you know, you put a pot of water on the stove, you turn the stove on, and that causes the water to boil and evaporate, right? I said, well, as far as the physics is concerned, you put the water on the stove in order that its boiling should cause the stove to cool. The physics is perfectly happy with that explanation, okay? Why do we prefer the first explanation over the second? Well, because boiling water has proved to be evolutionarily valuable for survival, whereas cooling the stove, not so much, right? So there's kind of a built-in bias there. But anyway, that will take us a bit far afield, but I'm not the only person to harbor these doubts about causation. In fact, I'm in pretty good company. Bertrand Russell in 1913 said, you know, all philosophers of every school imagine that causation is one of the fundamental axioms or postulates of science. And yet, oddly enough, in advanced sciences such as gravitational astronomy, the word cause never occurs. He says, the law of causality, I believe, like much of what passes muster among philosophers, is a relic of a bygone age, surviving like the monarchy only because it's erroneously supposed to do no harm. So maybe everything doesn't have a cause. And he kind of threw down the gauntlet to the physics world and said, you know, show me what basis you have for assuming that everything has a cause. So determinism, of course, doesn't make any sense without the notion of causation, right? So the two concepts are really tied together. And determinism proves in both physics and philosophy to be a really difficult problem to get your head around. Okay, this is a nice quote from a primer on determinism by John Ehrman, where he basically wrote a whole book on determinism, and right in the preface says, I give up. I don't know what to tell you. You know, that's essentially what he's saying. So what really do we mean when we talk about determinism and causation? Well, we mean that things could turn out in multiple ways. That's sort of necessary, but that they turn out in some way. Okay? And there are several questions, right? When is the determination made of how they're going to turn out? How is the determination made, and why is the determination? And I think it's really important to keep these questions separate because they're really different questions. Right? I mean, the why might lead you to religious statements, for example, whereas the when probably not. Right? So these are different questions. So let's just focus on when, and this is something that I did in this book that was published 2 years ago called The Coevolution. So in that book, I tried to construct, using automata theory, the smallest possible universe in which we can talk about the difference between deterministic and non-deterministic systems. So I had a tiny, tiny universe that comes into being with a little bang. It's a tiny universe, so it's not going to be a big bang, it's a little bang, right? And when it comes into being, there's two possible ways it can come into being. It's in being one or it's in being two. If it's in being one, then the entire behavior of the universe is to tick. If it's in being two, then the entire behavior of the universe is to top. Okay? Those are the only alternatives. And the resolution of the alternatives here is made when the universe comes into existence. So once it comes into existence, we have a deterministic universe. So analogously, some physicists believe that the trajectory of the physical universe was determined at the Big Bang, and its entire behavior after that is entirely governed by these deterministic laws of physics. Right? That's a bigger universe, but the same principle. Now, you could have a rather different non-deterministic universe, right? Where we start out with it doesn't exist, there's no universe, the little bang occurs, but the resolution between tick and tock hasn't been made yet. And it gets made after the universe is in existence. The decision is made later, right? This is about when the alternatives are resolved. So in this book, I used some basic results due to Robin Milner, who's a very famous computer scientist, got the Turing Award. And he did a bunch of work in the 1980s in automata theory. And he showed, in fact, that it's impossible to tell objectively the difference between these two universes that I just showed you. You can't tell the difference by just observing. Right? It's sort of obvious in this case, right? Because in both cases, the behavior is either tick or tock. And if you see tick, you don't know which of these caused it. If you see tock, you still don't know which of these caused it. In fact, it's impossible to tell the difference by just observing. Okay, so objective observation makes it impossible to tell the difference between a deterministic universe and a non-deterministic universe. However, Milner showed it is possible to tell the difference if you use a subjective first-person interactive involvement in the system, meaning you interact with the system rather than just observing it. But interestingly, you can't actually tell the difference up to 100% confidence. You can build up your confidence up to an arbitrary level, but you can never get to 100%. Right? So I'm not going to give you the details of this argument because it's a little bit subtle and mathematical, but you can read my book if you want to really dive into the argument. It's really a fascinating argument, right? It says that it really calls into question this scientific ideal that all science should be done objectively without interacting with the system. Just observation, let the data speak for itself, right? It turns out there's some things you can't tell the difference. Okay. But on the other hand, if you look at the model, these two models, if you've got these two models in front of you, right, you can definitely tell the difference between the two models. It's obvious, right? So as soon as you're working with models, things become a lot easier as opposed to just working with the physical world, right? The upper one is deterministic, then the bottom one is non-deterministic. So if you define determinism as a property of a model, not as a property of a physical system, everything gets easier, okay? You could define determinism much more easily. A model is deterministic if given the initial state and the inputs, the model defines exactly one behavior. There's three words here that are highlighted and put in red that you have to define before you can even talk about determinism. So a lingua franca program is deterministic if what you mean by state is state values of the state variables in the program at a particular instance in logical time. If what you mean by inputs is the input events that are provided to the program and their timestamps, and if what you mean by behavior is the trajectory of valuations of the state variables and the sequences of messages that are exchanged between programs. A lingua franca program is not deterministic if what you mean by state is the temperature of the machine that's executing it, or if what you mean by state is things like the physical time at which a state variable changes value. The lingua franca program doesn't define that as being a deterministic system. So when you talk about the determinism of the program, you have to define these three terms before you can even talk about the determinism of the model. The lingua franca program is a model. And if you define these three variables, these three concepts in a particular way, you get a deterministic model where there is exactly one behavior. Right? That's the key high-level point that I want to make, is that it's very difficult to talk about determinism, right? You could write down a very simple program that just does hello world, and you could say, well, that's deterministic. All it ever does is print hello world. But it prints it on a screen in a particular color. What if you define part of the behavior to be the color that is, that it is printed in? Then the program is no longer deterministic. What if you define the physical time at which it prints the message as part of the behavior? Then the program is no longer deterministic. Right? So you have to define these terms before you can talk about the determinism. Now, I want to give you three examples of deterministic models that have proved wildly successful in engineering. In fact, that really underlie the information technology revolution. Single-threaded imperative programs are deterministic if you define these three concepts correctly. Right? We would not be doing all of our banking online if it weren't for the determinism of single-threaded programs. We just wouldn't. Right? Instruction set architectures are mostly deterministic. They're an abstraction of the hardware. Synchronous digital logic is deterministic. Right? What happens in the actual silicon is just a bunch of electrons sloshing around. If you include in the behavior where all the electrons are, it's not deterministic. Right? But if you talk about the logic behavior, then it is deterministic. These three deterministic models are really the bedrock of the information technology revolution. And their determinism is a key factor in that, in the power of these concepts, right? So what is the value of determinism? Well, one of the key properties that it has is repeatability, by definition. You give it the same input, you get the same outputs, okay? That enables testing. Remember last time I talked about these untestable programs that use the Toyota style of design. Basically, the way these programs work is you could define what all the sensors are going to give you. And the fact is that the programs didn't specify one behavior. They specified a very large number of possible behaviors, given exactly those same inputs. which makes them very hard to test. You can't use standard regression testing techniques where you just check to see if you get the right behavior, because you have to check the behavior against a very large number of possible behaviors. Another very important property of deterministic models is that you can form consensus. Again, think about banking, right? When you do a bank transaction, you come to a conclusion about the effect that it will have on your bank balance, and the bank comes to the same conclusion. If it didn't, if that were not true, then banking would be kind of a problem, right? So being able to form that kind of consensus is a really nice property of deterministic models. Predictability. People often focus on this as a key property of deterministic models, but it is not a property of deterministic models. Not all deterministic models are predictable. Here's one of my favorite examples. This one was published by Ted Lewis and McGregor. Ted Lewis is a colleague of mine at Berkeley. They looked at a very simple thought experiment. Two idealized spheres that are moving around on a table and colliding with one another. This is a model, right? We're talking determinism of a model. Right? These are perfect spheres. They bounce perfectly off of one another without losing energy. They bounce perfectly off the walls. Okay, so very idealized model. None of the messiness of the physical world. Model is perfectly deterministic. Right? Write down the equations, and the equations have exactly one behavior. So he did this thought experiment, right? So he said, well, okay, is this model predictable? And he did a very simple calculation, which was how precisely does it need to know the initial conditions of the walls in order to be able to predict their position after 35 collisions? Okay, just 35. Perfectly deterministic model. Okay. So he did that calculation, figured out that there's this, you needed to know position within a certain resolution. Okay. Physical distance. He said, okay, well, let's assume that in some physical system, we're going to determine the initial position of these masses optically. Then what's the wavelength of light that we need to have that precision? And he found that a single photon of that light has more energy than is posited to exist in the universe. That's the precision with which he needed to know the initial conditions in order to be able to predict the positions of the masses after 35 collisions. That means it's not predictable. The model is perfectly deterministic, but you cannot, even in theory, predict the positions of the balls after 35 collisions. So this phenomenon is called chaos. It was really first established by a meteorologist. Edward Lorenz was a professor at MIT in the meteorology department. And he was looking at things like when thunderstorms form, and was using very sophisticated thermodynamic models in the 1950s. Thermodynamics was pretty well understood by the 1950s. And he was finding that he was also one of the pioneers in doing computer modeling of weather systems. And it was very frustrating to him that these computer systems were pretty ineffective at predicting the weather more than a few days in advance. And he was, working on this and saying, well, there's something wrong with the way that something wrong with what we're doing on the computer. The models are good. And then he found that actually the models intrinsically were chaotic, and they have this property that subsequently got known as chaos, which is that an arbitrarily small perturbation in the initial conditions or in any piece of the computation has arbitrarily big effects in the future. And that's in the model. Okay? It's an intrinsic property of the differential equations that are used to describe the thermodynamics. The model itself is unpredictable. Forget the weather itself, right? The model is unpredictable. So even if the model is perfect and perfectly emulates the physical world, it still cannot make the predictions of the weather more than a few days in advance. Okay. If you think about this, you know, a lot of people, when they confront this, really don't completely get it, right? They say, okay, a differential equation, that's a completely deterministic thing. You can write down this differential equation, it doesn't have very many variables. It's not a big thing, right? We should be able to analyze this. This happens to be the Lorentz attractor, which is a famous chaotic system due to Edward Lorenz. If you try to calculate the behavior of this on a computer, this happens to be a computer-generated plot. Is it actually the behavior of that differential equation? No. After a few iterations, it's not even close. It can't, because the computer is, first of all, discretizing the steps. That introduces arbitrarily small perturbations. No matter how fine you make the discretization, you're still going to get arbitrarily small perturbations, which importantly have arbitrarily big effects in the future. Okay? Meaning that because of those perturbations, knowing the position of one of these dots at one time will tell you nothing about its position sometime in the future. So determinism and predictability are not the same thing. There's this very nice paper from EMSOFT in 2015 where Lothar Thiele showed chaotic behavior in what looked like perfectly deterministic, idealized real-time scheduling problems. Okay. And this was, you know, sort of shook up a lot of people, right? Because these were using basic scheduling principles for real-time systems, and we showed that you could get chaotic behaviors anyway. Deterministic models enable fault detection, right? Faults can always occur. If you have a deterministic model and your physical realization fails to match the deterministic model, you treat that as a fault condition. You have a single-threaded imperative program. It's a deterministic model. If the program doesn't behave the way the program says it should, if the program execution deviates from that, you have a fault, right? The hardware has done something wrong. Alpha particle flipped a bit or something went wrong, right? If you know what the right behavior is, you can detect the fault, which means you can do fault handling. If you don't know what the right behavior is, you can't detect the faults, right? Simplicity, of course, one correct behavior for each input. Unsurprising behavior is under the principle that boring is good, which for a lot of safety critical systems, that's exactly what you want, right? You want to give a demo that says, look, nothing bad happened, right? Composability, if the component behavior is clear, often your composition behavior will also be clear. Now, one thing I want to point out is that non-deterministic models also have value. Okay, so this isn't a statement that all your models should be deterministic. No, there's lots of situations where non-determinism is helpful. So non-deterministic abstractions may be easier to understand, right? If you don't have to describe all of the possible little pieces of a behavior, but you say, well, the behavior is going to fall in this class. That might be a lot easier to understand than something deterministic. So abstraction is a relation between models, and there's a corresponding refinement relation, right? So, for example, if you have a program, a computer program, you might compile that into a lower level computer program. Assembly language program, for example. The assembly language program and the original computer program are both models. They're models of how you want the electrons to slosh around, basically, right? But they're still models. So non-deterministic models are useful for dealing with uncertainty about the world. So, for example, if you're designing self-driving cars, you probably don't want to try to model the driver as a deterministic model. Okay? That's a very difficult thing to do with humans. You could also use non-determinism for modeling uncertainty about the design. Maybe you don't know yet what the right design is. So you leave some wiggle room in your design. So this brings me to the most audacious slide, which is really the one that I'm going to close with today, which is the one concept that I first really discovered when I was writing this book, Plato and the Nerd. So there's a distinction between models and the physical world. Okay? Immanuel Kant is famous for having really first clarified this idea, right? Das Ding an sich. It's the thing in itself, is the physical thing, right? And then there's the model of the physical thing. Well, when I was writing this book, I realized that there's a symmetric relationship between science and engineering. So when you're doing science, you're trying to construct models that match the physical thing. When you're doing engineering, you're trying to construct physical things that match models. Right? So, you know, you're making silicon chips. You're trying to get the silicon to match the synchronous digital logic model. If you're doing science, you're trying to model the sloshing of electrons in the silicon. Those are two different things. Okay? And they're very complementary. And they're especially powerful when you use them in combination. Okay? So when you're doing relations between models, you're doing math. So here you have it in one slide. Okay? Engineering, math, and science explained. And the relationship between them. Right? It's all about relations between models and relations between models and things. So another way to put it, just to put it succinctly, in science, the value of a model lies in how well its behavior matches the physical system. In engineering, the value of a physical system lies in how well its behavior matches the model. I give you a piece of silicon that doesn't realize the synchronous digital logic, the silicon is junk. There's not necessarily anything wrong with the model. Right? It's a different conclusion. Another way to think about it is a scientist asks, can I make a model for this thing? And an engineer asks, can I make a thing for this model? Okay. So a lingua franca program is an engineering model. And the whole goal is to make a physical system that emulates that model. And of course, you want to be able to have it be efficient and cost effective and perform well and all that. Right? So you have all those requirements, but you want the physical thing to behave like that model. And of course, you can never do it perfectly. There's this famous quote from George Box, who said, essentially, all models are wrong, but some are useful. So as I was writing this book, it came to me as an aha moment. He's talking about scientific models. There's a corresponding statement for engineering models. Essentially, all system implementations are wrong, but some are useful. A physical implementation never perfectly matches your model. And it always has the possibility of deviating from your model's behavior. But if you can make those possibilities rare enough, it becomes a useful system. Okay? So these two kinds of uncertainty are all about this relationship, this asymmetric relationship between engineering and science. There's other advantages of non-deterministic models. Sometimes they're useful in security. I learned about a project that had, in San Francisco, there's this company that has a whole wall, about the size of that wall, with lava lamps in it. And they have cameras aimed at this, and they're using the lava lamps to synthesize keys for encryption. Because they're very unpredictable, chaotic systems. Don't care scenarios, and there's of course situations where you want surprising behavior, right? Where boring is bad. in which case non-deterministic models are going to be useful. Okay, so I think I'll close there. I do have a bit more that I could say about the limits of determinism. And one of the ones that I'm most interested in is this incompleteness result. But I'll just tell you what it is, and then we'll stop there because I don't want to run over time. I published a paper in 2016, 6 years ago, that shows that any set of deterministic models that's rich enough to encompass Newton's laws and also allows discrete behaviors is topologically incomplete. It means it has holes in it. Okay. The conclusion of this is a mathematical statement that says that any modeling framework that's deterministic, if it's rich enough to describe the physical world, it has to admit the possibility of non-deterministic behaviors. And that's a mathematical result about models. In my view, it really undermines the physics principle of determinism because physics is all about models of the physical world. And it says that you will never have a modeling framework if it's rich enough that is completely deterministic. So there are limits to deterministic modeling, but we'll not go into that detail. Okay, so let's stop there. So on Monday, I'm going to talk about time, and we'll do a lot of some hands-on lingua franca programming and show how timing behavior is handled, and I'll talk a bit about the nuances of deadlines, and also talk about some open problems that we have with deadlines in lingua franca, which if you're looking for research projects, there's some nice ones there.